Hello guys, welcome to the online teaching portal of the Catalyst, an institute where we want to interact with you guys and give you the concept on demand. We'll try to give you the answer as per your requirement and we'll give you the concept based on the competitive exam approach. To start with, I have taken some of the questions from KVPY 2015 exam chemistry portion and will guide you through them and give you the idea how the concept is being made for such questions, and you may build upon your theory for the coming up paper. So to start with, the two questions belongs to 2015 KVPY paper SBSX stream 1 marks. So the Lewis acid strength of boron trihalide has been discussed in question number 41. What are Lewis acids? Before jumping into the conclusion, what is the answer and how do we go, just try to figure out what the basic concepts behind this and what is the need to give such kind of a question in the exam. What is Lewis acid? Lewis acids are the species which accepts electron pair and base which donates electron pair. For example, boron halide, trifluoride, trichloride, whatever it is Lewis acid because it is having empty p orbital in which they can accept the lone pair of Lewis base such as ammonia. It is very prominent Lewis base. In case of acid strength of boron trihalides, boron tribromide, chloride, fluoride, and actually iodide is also considered. Let me give you idea of boron trihalide structure. This is sp2 hybridized orbital which boron is having, and it is directly associated with p orbital of halide. 3 orbital of halides are interacting with sp2 hybridized orbital of boron to form this kind of a structure which is trigonal planar. The order of acid strength of fluorine of boron trihalide appears to be boron trifluoride. Boron trifluoride is most acidic, then boron trichloride, then boron tribromide as per the electronegativity of halide involved, because acidity of any species depends upon how well the electron pair is accepted and the product is formed. However, in this case, nature of boron halide bond needs to be taken into account. sp2 hybridized boron halide bond, this one, having pz orbital overlap which is strongest in BF3 because of same size of pz orbital. Hence, it is the most stable and difficult to break. Boron trifluoride is having pz orbital which are similar in size for boron and fluorine both. So they form strong bond among the halides and it is difficult to break. Fine. Therefore, BF3 is the weakest. Now, here comes the point. Boron trifluoride is the weakest acid among boron halides. Bigger the size of pz orbital, less will be the overlap and bond will be relatively weak. So as the pz orbital size of halide, fluorine, chlorine, then bromine, the size of this pz orbital is increasing, the bond formation is weak and it is easy to break. So here comes the idea, boron tribromide is most acidic, then boron trichloride, then boron trifluoride. So this is the correct order. Option is C. Boron triiodide may also be considered and it will come like this. Boron triiodide. Boron trifluoride, you can see that all the p orbitals are of same size. So they are more closely bonded with empty p orbital, pz orbital of boron, and the strong bond formation is taken place. In case of boron trichloride or bromide, as the pz orbital of chlorine and bromine is higher in size, so 2p, 3p, 4p, like p orbital size is increasing. So there would be a difficult interaction in between the pz orbitals and the bond formation is relatively weak. When it is a weak bond, it is easy to break and get into the system. In case of boron trihalides, boron iodide is strongest Lewis acid. Given the condition, then BBr3, BCl3 and BF3 is taken place. Going to the next question of this paper, isoelectronic species. Now, what do one understand by isoelectronic species? Iso means same, electronic means number of electron. So isoelectronic would be simply meaning the same number of electrons in species. This is rather the simple question, but I came across some difficult question of that sort. So it would be good if we get the idea of this question in detail. So O2 minus. Oxygen is having atomic number of 8, zinc is atomic number 30, magnesium atomic number 12, potassium atomic number 19, and nickel is having atomic number 28. Now, what is some element A plus means? Whatever be the number of electrons in element A would be less than 1 by A plus. Like sodium is having 11 electron in its kitty. Now Na plus would simply be meaning 11 minus 1 electron gone, it is equals to 10. In case of magnesium plus 2, it is 12, minus 2, it is 10 only. Now once it comes to oxygen minus 2, that means 8 electrons of oxygen and 2 more electrons, that means plus 2 electrons of outer electrons which has come to the outer shell of oxygen. This comes to be 2, that is 8 plus 2, 10. It is a simple question. We can say oxygen is having 10 electron and magnesium is also having 10 electron. It is right. Option is B. But we have to check all the options. Zinc plus 2 means it is having 30 minus 2, it is 28 electrons. Fine. Magnesium 2 plus, it is 12 minus 2, it is 18 electrons. Then potassium plus is 19 minus 1, it is 18 electrons. Fine. Nickel 2 plus is nothing but 28 minus 2, it is 16 electrons. So we can simply say 2 minus is 10 and this yes, magnesium 2 plus is also 10. So this is 10 electrons, this is 28, this is 18, this is magnesium is 10, nickel is 26 electrons. So our option is B, which is magnesium 2 plus. Now moving on to question number 43 of this same question paper, the bond angle of HCH, HNH, HOH in degrees, methane, ammonia and water. It is very classic example of tetrahedral structure. All the three having a tetrahedral structures in which lone pair bond pair interaction is taking place and it is taken into consideration. Now hybridization of these three molecules are same. It is sp3 hybridized orbital, Ab4, Ab3L or Ab2L2. It is very simple. Now let's have a look at the structures of all three compounds. This is CH4 methane. Carbon is tetrahedrally associated with 4 hydrogen atom at an angle of 109.5 degree, which is a regular tetrahedron. All the bond angles, bond length are same. The angle would be highest 109.5 degree. We have to consider one more thing, that is lone pair repulsion is highest, then lone pair bond pair repulsion, then bond pair repulsion. So we may consider that bond pair repulsion in methane is very low. So regular tetrahedron has been formed with an angle of 109.5 degree. Next, under consideration of the molecule of ammonia. This is ammonia. Ammonia is having one lone pair on top. So it is having tetrahedral geometry, but shape is actually trigonal pyramidal. 3 hydrogen nitrogen bonds would be on a lower side, on the downside of the lone pair on the top. Now as we can see, this lone pair bond pair repulsion is higher than bond pair repulsion. So this lone pair will try to push these bonds down. Angle would be a little lower and the angle is 107.1. And finally, water molecule. Example, there is a regular tetrahedron like type structure in which 2 lone pairs and 2 bonds pair are there. When 2 bonds pair are there, lone pair and lone pair repulsion would be very high. So what will happen is 2 oxygen hydrogen bond will be on a same plane and these two lone pairs would be above and below the plane. It would be a 3D structure, but oxygen hydrogen would be on the same plane, so they will form bent structure, and this two lone pair, one above and one below the plane, would form bent structure. Lone pair repulsion is higher, so they try to bend it down and make angle of 104.5. We may simply say that this is AB4, AB3L or AB2L2 type structure of same sp3 hybridized. Answer would simply be decreasing order of the angle, which is option B. 109.5 degree for HCH angle in methane, 107.1 for HNH angle for ammonia, 104.5 for HOH bond angle in water. Moving on to the next question, question number 44. In alkaline media, the reaction of hydrogen peroxide with potassium permanganate produces a compound in which oxidation state of manganese is. It would be rather easy to understand how they work in acidic and basic media. Potassium permanganate, it is KMnO4, which is simply may written as KMnO4 minus. Mn is having plus 7 as oxidation state. How do we do that? Manganese X plus 4 into minus 2 plus 1 of potassium is equals to 0. So X minus 8 plus 1 is 0. X is equals to plus 7 oxidation state for manganese. MnO4 minus goes to Mn plus 2 state in acidic media. Always remember this. A 5 unit change in oxidation number is 5. In acidic media, MnO4 goes to plus 2, in which oxidation number change is plus 5. In case of MnO4 minus plus 7 oxidation state, it is alkaline media, or rather neutral also. It simply goes to MnO2. Oxidation number would be plus 4. How do we do that? MnO2, it is X plus 2 into minus 2 is 0. X is equals to, rather X minus 4 is 0. X is equals to 4. Plus 7 MnO4 goes to MnO2. Change in oxidation number would be 7 minus 4, which is plus 3. Answer is plus 3. C answer. Hydrogen peroxide with potassium permanganate produces a compound in which oxidation state of Mn is plus 3. It is rather easy to learn than understand that MnO4 minus goes to MnO2 in case of the alkaline media.